We talked about two types of strains. We had torsional strain, that's between the bonds, the repulsions of the electrons in the bonds, and we talked about steric strain, that's the repulsion between the atoms or two large groups in that conformation. And we said that the best way to eliminate or reduce steric strain is to have an anti or a staggered conformation. And of course, you eliminate torsional strain when you also have a staggered conformation. However, when we talk about rings, we encounter a third type of strain, and that's called an angle strain, or what we call a ring strain. An angle strain is an increase in energy when the tetrahedral bond angle deviate. Angles deviate from the optimum angle of 109.5. 109.5 degrees is the most important angle, okay, that you need to know in this class. 109.5 means stability for the sp3 hybridized carbon. So if we look at the ring strain in terms of energy, and remember, higher energy means less stability. For cyclopropane, we notice that it's at 27.6 kilocal per mole. So that's high, actually. That's high. We notice that when we go to cyclobutane, it is 26.2, so it's going down. You notice that the angle is kind of expanding and it's not as strained as this one. And if you go to cyclopentane, the angle goes down significantly to 6.3. And then with cyclohexane, it's actually 0. So you're like, okay, well, I don't see anything. It's going down. But then you might expect that if you go to cycloheptane, that the angle might be 0 or even more stable. Nothing, of course, is less than 0, but it goes back up to 6.4. And if you have cyclohexane, it's a 9.9. If you have a cyclononane or nonane, that's a 12.8. So there must be something happening with cyclohexane. And again, as we defined, angle strain is when the angles between the carbon-carbon bonds are constrained by the size of the ring to be much smaller than the ideal tetrahedral angle, which is 109.5. So there are, once again, these are the three strains that we defined. Now let's look at cyclohexane. What's happening? With these, again, the angle is deviating from 109.5. With this one, it's not. So our focus will be on cyclohexane. So here's cyclohexane. And cyclohexane is a ring that looks like a hexagon right here. Now you need to remember that there are two H's on each carbon, right? Two H's and two H's and two H's. So this is important. We will not simply forget what's attached to those carbons, especially when they are hydrogens, because they are implied. So I'm showing you here. Well, the reason why it's very stable is because cyclohexane takes the conformation of a chair, and that's the most stable conformation. So this is a chair conformation. How does it look like? It looks like a chair where you actually have this person right here sitting. Here's the headrest. That's this going up, this flap right here going up. And then this is the footrest that is actually going down. And in between is this where this person is sitting. Of course, there are no lines here connecting them. So kind of that's why organic chemists call it the chair conformation. Where are you looking at it? From what angle to say that it's a very stable? Well, you're looking at this one right here. Here's the eye. And you're looking at this carbon right there. So again, here's the eye right here. Again, pardon my drawings. And if we do a Newman projection on this, we'll notice that all the H's, so again, you have to really work on imagining this right here, is we'll see that all the Newman in the Newman projection, all the H's, look at them right there, are staggered. So all H's are staggered. And what does that mean? Zero torsional strain. Right here. They're all staggered. What else is also happening here is that all the bond angles are actually 109. All bond angles are 109.5. So that means we have zero angle strain. Right here. So beautiful works out to be very beautiful. Now there are two kinds of H's that you need to know. You need to know very well. There are what we call the axial H's. Those are the up and down. So I'm going to use blue. So once again, here's the axial, another axial, another axial, and another axial. You see them also here. Here, I mean. Now, these are called in blue. Those are called in blue here. Those are called axial H's. And these are simply up and down. They are up and down. The other ones, the red ones, have a name. Since you have an axis and you have the equator, these right here have a name. They're called equatorial or equatorial. So these are called equatorial. H's. And again, they kind of like point out from the ring. They point out from the ring. Now, if you do a ring flip, although we're not going to spend too much time on this, in a ring flip, you will actually have a switch between the axial and the equatorial. I'm not going to really go deep into this because this might be very confusing, but if you do a ring flip, you will actually basically, you take this and you just flip it now, flip this, like raise this up and bring this over. You will actually have a switch. So we're going to label them for now, but once again, all the blue that you see here are now going to be these. So this class has a lot of visual material. Again, get in the habit of visualizing stuff because you will have to do that. And now your equatorial became, in this case, the axial. So here's the red. It's a good, again, exercise to go through. Very well. So of course, for cyclohexane, both chair conformations have equal energy. The energy barrier between them is a 10.8, which is low enough at room temperature. There's about 10 to the fifth, 100,000 flips per second. That's how rapid it is. So let me just again write down here that in the chair flip, the axial becomes equatorial, and equatorial becomes axial. So this is very critical to remember. Axial becomes equatorial, and equatorial becomes axial. So in order to go from one chair conformation to another, the cyclohexane must go through a half chair, a boat, and a twist boat conformation. And as I said, here's a more description of those axial and equatorial H's. So around the equator and along the perpendicular axis for the axial. So in order for you to go from one flip to another, from one chair conformation to another, to do a flip, it has to go through all of these, believe it or not. And in this case, what you have is you have to go through a half a chair, twist boat, a boat, half a chair, and of course back to the chair. All you have to remember from this is that, again, these are the highest, these two are the highest energy, the half a chair. The boat is in the middle, and the reason why boat is bad is because if we draw the H's, again, there's a chance for steric strain right here. Steric strain. These are somehow in the middle, the twist boat, but the lowest in energy, of course, is the chair conformation. And that's our most stable one.